Hello students, today we will discuss measurable functions. Earlier we have studied measurable sets. Now how to define measurable functions over measurable sets. So let us see definition of measurable functions. An extended real valued function f defined over measurable sets E is said to be measurable in the sense of Liebig if E, which is defined as collection of those elements of E for which fx is greater than a. Again I am repeating this. This collection is defined as set of all those elements of E, set of all x belongs to E for which the image of these elements under f is greater than a. So this collection is measurable. If this collection is measurable where a is extended real number. So if this collection is measurable, then f is said to be measurable. Then this real valued function f is said to be measurable over E, over measurable set E. So more clearly this definition says that if f is measurable function, if for every real number a, the inverse image of a infinity, open interval a infinity under f is measurable set. So this is the definition of measurable function. Now a theorem says that f be a measurable function defined over a measurable set ER for all natural number R a natural number, then f is measurable on E, where E is enumerable union of these measurable sets ER. So we have to prove this function defined over ER is measurable. So let us see proof of this theorem. Here we have taken E as enumerable union of measurable sets. And the part of measurable sets we have studied enumerable union of measurable set is measurable. So also given that the set x belongs to ER, set of all x belongs to ER such that fx is greater than a is measurable for all real numbers a and natural numbers R. Now we define E f a, and this is equal to union of ER, R from unit taken from 1 to infinity, f of x is greater than a. This means this is union of all ER for which fx is greater than a, and we have taken f is measurable on each AR, each ER, f is measurable on each, f is measurable on each ER. So thus we conclude that f is measurable over E, which is enumerable union of ER, hence f is measurable on whole union in f is measurable on E. Now we will define characteristic function. So characteristic function phi a of set A is defined by phi a x is equal to 1 if x belongs to A, and it is 0 if x does not belongs to A, but x belongs to complement of A. So this is the definition of characteristic function where A is subset of measurable set E. Now we will discuss some theorems. So these four definitions, let us see these four definitions of measurable function. So this theorem says that prove that definition for measurable functions can be replaced by other three definition, prove their equivalence. So we see these four definitions for measurable function, and we will prove all these four definitions are equivalent. So let us see proof of this theorem. The four definitions for a function f to be Liebig measurable are: number 1, E where f is greater than a, E where f is greater or equal to a, f is less than a, and f is less or equal to a. So if any of these sets are measurable, we want to prove their equivalence. So suppose in the continuation of the proof, suppose first implies second, means these conditions satisfied, and we have to prove this one. So how to define this one? E f greater or equal to a means intersection from n from 1 to infinity, E f greater than 1 minus a minus 1 upon n, and we have assumed this set is f is measurable on this set, and this collection is measurable. So see here, this is the intersection of E for which f is strictly greater than a minus 1 upon n. So therefore this collection is measurable, being an enumerable intersection of measurable sets. This is enumerable intersection of measurable sets. Now we will prove second implies first. So since second implies first means we have assumed this condition, and we will prove this one. So how to define this one? So this is defined here. Since E f greater than a is equal to union n from 1 to infinity, and E f greater or equal to a plus nh. This is f greater than a, and we can add some terms in a. So this will be equal to, so f greater or equal to a plus 1 by n. So since f is measurable on this collection and this collection is measurable, therefore the whole collection, this one is measurable, and therefore this one E f a is measurable, being a countable union of measurable sets. Next, second implies third, and second implies third. So we assume this second, and we will prove third result. So second implies third says that since third f less than a can be defined as E f greater or equal to a complement. So complement of this one is this. So also we know that set is measurable if and only if its complement is measurable by the measurable properties of measurable sets. So its complement is measurable. So since this part is measurable, that's why this one is measurable. Thus if we assume this part is measurable, then this one is measurable, and if we assume this part is measurable, then this part is measurable. So other side will also be measurable. Similarly, first implies 4. Now we will prove third implies fourth. Since E f less or equal to a, third implies 4, f less than a and f is less or equal to a over e. So f less or equal to a can be defined as intersection n from 1 to infinity E f less than 1 plus 1 upon n, and we have assumed f less than a is measurable. Therefore this collection is measurable, being arbitrary intersection of measurable sets, and therefore E f a is measurable. Now fourth implies third. So fourth implies third, since f less than a, this is enumerable union of, this is union of E f less or equal to a minus 1 upon n, therefore being an arbitrary union of measurable sets, and E f a is measurable. So all these four definitions says that if f is measurable, then E f is equal to a is measurable, because f is, in case of f greater than a is measurable, f greater or equal to a is measurable, f less than a is measurable, f less or equal to a is measurable. So by all four conditions, this implies that f is measurable, then E f is equal to a is also measurable. Now next theorem, this is the important theorem, a constant function over a measurable set is measurable. A constant function over a measurable set is measurable. So let us see proof. So we consider a measurable set E and f being a constant function defined over E. Now by the definition of the measurable function, this can be written as E f greater than a is equal to E if this C is greater than a. The C, what is C? This is the constant. C is greater than a, and this is phi if C is less or equal to a. So this definition gives us these two conditions, E and phi, and since we have taken E as a measurable set and empty set is also measurable, therefore this collection is, this is measurable, this means f is measurable on E. This means the constant function is measurable over a measurable set. Next theorem, if f is measurable over a measurable set E, then f is also measurable over any measurable subset A of E. This is also a nice result. So suppose we are taking a measurable subset of a measurable set E. Now we want to show that if f is measurable on E, then f is also measurable over A. So how to define a function f over A? So this is defined by f over A is defined by, this is f E, f defined over E, this is fx is greater than A intersection A. Thus fa is measurable being intersection of two measurable sets, because A is measurable and E is also measurable, and this definition, this is the intersection of two measurable sets, therefore this part is measurable. So a note is here, f greater than E is measurable since f is measurable on E. So this is by the definition of measurable sets. The next theorem says that if fx and gx are measurable functions, then maximum of these two functions and minimum of these two functions are measurable. So how to define maximum over a set or a minimum over a set? So to prove this theorem, we have defined here a maximum of these two functions over set E. Maximum of these two functions f and g over E is defined as, this is the E for which f is less than A intersection E, the function g defined over E where gx is less than A. And since f and g both are measurable functions, both are measurable over E, and therefore by the four definitions given in previous theorem, these two parts, this one and these one are measurable. So their maximum defined by this one. So intersection of two measurable set is measurable. Therefore this maximum of these two functions f and g is measurable. Similarly, we can prove that the minimum of these two are measurable. So its alternative part is given here. The students can prove by this condition minus of these two. Now next theorem. Let f be measurable function defined over a measurable set E. So we have to show that C into f plus C mod of f square 1 upon f is taken in case when f does not vanishes on E. So all these are measurable. We have to prove that all these are measurable. So we have taken C as a constant here. This is also important theorem. So let us see proof of this theorem. We have to, first of all, we will prove CF is measurable. So how to define CF over set E, over measurable set E? So to prove that CF is measurable on E, we have how to define the function CF over E. So this is CF is greater than A, and this is defined by E f greater than A by C if C is positive, and this is f less than A by C if C is negative. And for C equal to 0, and for C is equal to 0, then CF is equal to 0, we will discuss next. So here for C greater than 0 and C less than 0, this part is defined by these two. So since f is measurable over E, and by four definitions given earlier, this one also measurable. So in both the cases, this CF is measurable, as A by C is also a real number, and the case which we was discussing earlier, if C is equal to 0, then CF is equal to 0 for all x belongs to E. In this case, CF is a constant function, a fixed value. This is giving the fixed value CF is equal to 0. So, this is constant function, therefore, CF is a measurable by the previous theorem. A constant function is measurable. Next, we will prove f plus c is measurable. So, to prove that f plus c is measurable, we will define f plus c, a function f plus c over set E as f plus c greater than a, means f is greater than a minus c. A minus c being a real number, and that is why this is the measurable set. And since this is a measurable set, that is why this one is measurable, and as this one is measurable, so c plus f is measurable over E. Next, we will prove mod of f is measurable. Next, we will show mod of f is measurable. So, how to define mod of f, mod function over E? So, mod of f is less than a, and this is defined by, this is phi if a is less than 0, because mod of a function or a mod of a number cannot be less than 0. That is why, so mod of f, if mod of f is less than a, so this gives us phi if a is less than 0, this one, this is less than 0, and this is E f less than a intersection E f greater than minus a if a is greater or equal to 0, as we know that. So, mod of a number is less or equal to mod of a is greater than minus a and less than a. That is why we are writing in intersection of these two parts, and since f is measurable over these two parts, f is this is measurable, that is why this collection is measurable. So, we have written here, since E mod of f is less than a, which is defined by this, since phi is also measurable, phi is measurable, and these two separate parts are measurable and their intersection is measurable. That is why this one is measurable, since the union of, so I think here should be correction, this is the intersection of two measurable sets is measurable, hence mod of f is measurable. Next, f square is measurable. This is important result. F square is measurable. And how to define f square? Square of a function over measurable set E, and this is defined by, this is E if a is less than 0, and if a is greater or equal to 0, then this is mod of f is greater than root of a, and since mod of f is greater than root of a is defined as, so I am writing, please correct here, this is the union of this one, please correct here, union of, so a and greater than minus of a, yes, so make union sign there. Next, E f square a, this is defined by these two parts, this is E if a is less than 0, and if a is greater or equal to 0, then mod of f is greater or equal to, greater than root a, and this part is again elaborated as, this is the union of these two parts, greater than a and less than minus of a, less than minus of a, and therefore E f square a is equal to E if a is less than 0 and greater or equal to 0. So, f greater than a root a union f less than minus root a, and since E is measurable, f is this collection is measurable, this collection is measurable, so union of these two is measurable. So, in both the cases these and these are measurable. So, we are writing here f is measurable over a implies that E f greater than root a and E f less than minus root a are measurable sets, implies that their union are measurable, hence this f square defined over E is measurable. And last result, we have to show 1 upon f is measurable if f vanishes nowhere on E. So f vanishes nowhere on E means fx is non-zero for all x belongs to E, and this shows that 1 upon f exists. Now how to define this function 1 upon f over measurable set E, and this is defined by 1 upon f greater than a is equal to E set of E fx greater than 0 if a is equal to 0, and this is the intersection of these two parts E f greater than 0 intersection E f less than 1 upon a if a is greater than 0, and E f less than 0 intersection E f less than 1 upon a union E f greater than 0 if a is less than 0. So for all these three cases if a equal to 0, if a is greater than 0, and if a is less than 0, these three cases arises. And since f is measurable over E, so this collection is measurable. This is the intersection of two measurable sets, and this is the intersection and union of measurable sets. So this means this is finite union and intersection of measurable sets, hence the function 1 upon f is measurable over E. So this was the proof of this theorem. Thank you.